So here we go for a nice and sweet and concise summary of the semigroup stuff. The first of all, we talked about strongly continuous semigroups. And important here is, of course, a semigroup property that T of t plus s is T of t times T of s. This is a property you not only find here in the function analysis. This is something which is often used also in probability or in Lie group theory or in many, many different areas of mathematics. At 0 we have the identity, and then the map T maps to T of t is continuous at 0, which then implies it's continuous everywhere, like you showed in the homework. If it's a continuous semigroup, it has a growth law, an exponential growth law with growth rate omega, and then there's a bound m. And then we have seen that we always desire this m to be equal to 1, so then we have simpler estimates, and I come to that in a second. So the infinitesimal generator, this leads back to the semigroup triangle, is given as the differential quotient of the semigroup. So this relates t to a. And then it satisfies the differential equation. And this is basically the main reason why we do all this, because we want to use it to analyze differential equations. Then the inhomogeneous problem, if you have an f there, we can use the variation of constant formula with the semigroup. And this is a formula you should actually really remember. It is, again, useful wherever you go. So then Hille-Yoshida does the reverse. So then we start with an operator A, and then we find out when is it a generator of a semigroup. So when can we say T of t is e to the at? And the answer in Hille-Yoshida is A needs to be closed, dA needs to be dense domain, and then for lambda bigger than omega we have like this resolvent estimate for each exponent n, so for all n. But from the proof we found two very, very nice formulas, and they get one of my lovely pink boxes here. We found that t is the limit of identity minus t over n a. Where is the a? A to the minus n. Here's a little typo. And the other one was the Laplace transform. And then this formula as well, where the resolvent is the Laplace transform of the semigroup. So these were two important formulas for our semigroup triangle. If m is 1 in Hille-Yoshida, then we obtain a simpler resolvent estimate, which we need to satisfy by 1 over lambda minus omega. Now, Lummer-Phillips is a special case for contraction semigroups, or here we call them quasi-contraction semigroups, where we have a growth estimate with a constant 1 in front. This is what we want to have. And then the conditions to be a semigroup are a little bit different. So A is closed and densely defined, same as before. But then we just need to estimate the real part of x, ax, with this growth bound omega. And we need to find one resolvent. Right? A little bit more general, we need to find one lambda 0 so that a minus lambda 0 I is onto. In most cases, we actually do find a lambda 0 where we can find the full resolvent. And then this will be onto anyways. Good. So then we have, so there was Hille-Yoshida and Lummer-Phillips, and then the third one of the big theorems was the perturbation result. A is a generator, B is bounded, so then A plus B is generator, and we get a growth bound, where then the omega is increased by the norm of B times the size of this M. So things got really, really cool, sweet, interesting, or complicated in analytic semigroups, because we were talking a lot about these sectors, right? And I plotted them out. So this is like the sector. Oh, this is a terrible picture. So then the resolvent set needs to be on the right, or actually the sector needs to be included in the resolvent set. Then we call this a sectorial operator. And we saw that the second derivative often has just point spectrum here. So this will very naturally be a sectorial operator. Okay, so what can we do with the analytic semigroups? Analytic semigroups have sectorial generators. Sectorial generators generate analytical semigroups. So they're really basically the same. And then here we found another formula which deserves a pink outline here. This one, right, this is also something for the semigroup triangle. The Cauchy integral formula for the semigroup, where now t has a complex argument, right? We write t of z. So this is very curious. As I saw this the first time, I was completely confused. The idea is that the positive real axis, the time axis, is just included in a small sector sigma delta prime. And so in the small sector, we can actually allow a complex valued argument in t. And the way to do this is to use a path integral over a suitably chosen path gamma e to the mu z times the resolvent of mu and a. And this was actually the cow in the semigroup triangle. Good. So we saw that too. And then a little bit more. So analytic semigroups satisfy a regularity estimate. If t is a little bit positive and not close to 0, then we have a good estimate for a e to the at, which then was directly used to show that the semigroup regularizes, so mild solutions become classical solutions. And finally, we've shown a second perturbation result where we can perturb analytic semigroups by operators that are dominated by A, that are dominated by this operator. They don't have to be bounded because A doesn't have to be bounded, but B of x has essentially to be less or equal A of x. Good. So that's it for the semigroup theory. I hope you are convinced that on the one hand it is a very interesting theory in itself, and there are lots of books where you can learn more. On the other hand, it is a rather useful theory to study applied mathematics and to study differential equations, in particular partial differential equations.